According to Newton's second law, an object at rest will continue to be at rest unless a force acts upon it. If we had a stationary particle at rest and we applied a force, it would start to move with an acceleration, and the magnitude of its acceleration can be obtained from the relation F equals ma. So we can say that for a particle at rest to experience translational motion, there must be a force acting on it, and the acceleration it gains is proportional to the net force applied on it. In one of our previous videos, we discussed torque, and we described it as the turning effect of a force about an axis. The greater the torque, the greater the tendency for the object to experience rotation. We can therefore say that for an object to experience rotational motion about an axis, a torque must be applied to it about that axis, and its angular acceleration is proportional to the net applied torque. In the translational case, we know that the acceleration is proportional to the net force and inversely proportional to the mass or inertia of the object. But what plays the role of mass in the rotational case? To answer this question, let's examine the very simple case of a particle of mass m attached to a very thin rod of negligible mass having a length r. This system is set up in such a way that the mass is allowed to revolve in a circle about the other end of the rod. We're going to apply a torque at this end, and our goal here is to determine the relationship between the torque applied and the angular acceleration this torque gives the particle. We can represent our torque as a force acting on the mass, and the magnitude of this force can be obtained from the relation torque equals force times distance or radius. From Newton's second law, we know that this force will tend to give the object a tangential linear acceleration according to the relation F equals ma. And from our equations on circular motion, we know that the tangential linear acceleration is equal to the angular acceleration multiplied by the radius of rotation. And so our force will be equal to the mass multiplied by the angular acceleration multiplied by the radius. If we plug this value of force into our relation torque equals force times radius, we get torque equals mr squared times the angular acceleration of the object. So here we've obtained a direct relation between the angular acceleration and the applied torque. The quantity mr squared represents the rotational inertia of the particle, and it is called its moment of inertia. So now we know the relationship between the net applied torque and the angular acceleration of a single particle rotating about an axis. But what if we have a system consisting of multiple particles? Suppose we had two masses instead of one, m1 and m2, located at distances r1 and r2 from the axis of rotation respectively, and we apply a torque to this axis of rotation. We can represent the torque with forces acting on the masses producing the same effect as the torque. And we can obtain the magnitudes of the forces F1 and F2 using the relation torque equals F1 times R1 plus F2 times R2. So again, from Newton's second law, we know that F1 is going to give our mass m1 a tangential linear acceleration a1, according to the relation F1 equals m1 a1. And a1 is equal to the angular acceleration of particle m1 multiplied by its radius r1. We can say F1 equals m1 times the angular acceleration of the first particle times r1. Similarly, for F2, we can say F2 equals m2 times the angular acceleration of the second particle times r2. Now, since the effect of the torque is to rotate the entire system, and the forces F1 and F2 will produce the same effect as the torque, both particles are going to have the same angular acceleration. And so we have our total torque equal to m1r1 squared plus m2r2 squared multiplied by the angular acceleration of the system. And this is the relationship between the applied torque and the angular acceleration of this system consisting of multiple masses. We can therefore say that the moment of inertia of this system of masses is equal to the sum of the moment of inertia of the masses that make it up. So I equals m1r1 squared plus m2r2 squared. And this is always the case whenever we have a system consisting of multiple masses, So we can generalize and say that the moment of inertia of a rotating body is equal to the sum of the moments of inertia of each particle of that body. And in shorthand notation, we can write this as I equals sigma mi squared, which can be expanded into m1 r1 squared plus m2 r2 squared plus m3 r3 squared, and so on. M represents the mass of each particle, and r represents the distance of the particle from the axis of rotation. And for the rotating body, the net torque applied to it is equal to its moment of inertia multiplied by the angular acceleration. This is the rotational equivalent of Newton's second law. We should keep in mind that the value of the moment of inertia of a body changes depending on the location of the axis of rotation. This is because the values of r for each particle will change depending on the location of the axis of rotation. Let's say we wanted to calculate the moment of inertia of a solid object about an axis, let's say a cylinder. It would be tedious to divide this cylinder into a large number of smaller component masses and then calculate the sum of the moment of inertia of each of these masses. In practice, we find the moment of inertia of objects using integration, but again, that's beyond the scope of this video. We know already that the moment of inertia of a body depends on its axis of rotation. This means that a body can have multiple moments of inertia because there's an unlimited number of axes about which it can rotate. The parallel axis theorem explains the relationship between the moment of inertia of a body about an axis through its center of mass and the moment of inertia about any other axis parallel to the original one. The parallel axis theorem states that the moment of inertia of an object around a particular axis is equal to the moment of inertia around a parallel axis going through its center of mass plus the mass of the object multiplied by the square of the distance to that parallel axis.